In the last video, we talked about how to determine the amount of energy released or taken in during a reaction and the enthalpy of a reaction. In this video, we'll talk about 4 different ways of communicating that enthalpy change. But before we look at the different ways we can communicate enthalpy change, let's look at the symbolism. Here we have the standard notation for the enthalpy of reaction. Here, the delta H denotes for the enthalpy change. The R in this case denotes what type of reaction. R stands for any type of reaction. However, if the letter R is related to C, that means a complete combustion. F is a formation reaction. D is decomposition. SOL is the enthalpy of solution when you dissolve an ionic solid. And DIL is for dilution. This is particularly relevant for diluting acid. The next symbol we're going to look at, let's look at the M. This little m here to the lower right hand side of the delta H means that amount is per mole, per 1 mole of the compound that you're interested in. The little degree sign indicates it's at a standard state. A standard state, if you remember from chemistry 20, is at 1 atmosphere and at 0 degrees Celsius. And the last symbol we're going to look at is the chemical symbol underneath the delta H, and that is indicating the substance that the enthalpy is referring to. The first way we'll communicate the enthalpy of reaction is the molar enthalpy of reaction. The word molar, it implies that we convert this into a per mole amount. This will be measured in the units of joules or kilojoules per mole. This is akin to molar mass, where we measure something in grams per mole. So, for example, let's say the standard molar enthalpy of combustion of methanol is negative 725.9 kilojoules per mole. It really means that for every 1 mole of methanol that you burn, you release that much energy. If you burn 2 moles of methanol, you will release approximately 1,450 kilojoules of energy. The way we denote this is using this symbol. Here we have the standard delta H notation. If you remember from our last slide, the M here indicates it is a per mole amount. The C is for combustion, and we have the methanol compound written on the bottom. In terms of calorimetry, when we calculate the reaction, remember it's going to be N, which is the molar amount, times the molar enthalpy of reaction of your compound equals Q. And Q in this case can be calculated using MC delta T. The second way we communicate enthalpy change is just as a enthalpy term, and we can write this number to the right of an equation. This number is per equation and not per mole, as we did before. So example here, sulfur dioxide and oxygen reacts to form sulfur trioxide. The standard molar enthalpy of combustion of sulfur dioxide is negative 99 kilojoules per mole. Here we have the complete balance equation. 2 sulfur dioxides plus oxygen yields 2 sulfur trioxides. We notice here that the coefficient in front of sulfur dioxide is 2, so that if we convert the molar enthalpy change into just a standard enthalpy change, we have to multiply the enthalpy change by 2 because the coefficient is 2. So therefore, when we write this out in the enthalpy change format, we have to write the enthalpy of combustion is negative 197.8 kilojoules. This was this number, 98.9, multiplied by 2. Again, because it's 2, because there's 2 moles of sulfur dioxide. The third way we will communicate energy change is having the energy as a reactant or as a product in our balance equation. In this case, we're going to use the enthalpy per reaction, the delta H R, the reaction, that we calculate using method 2. Remember, for an endothermic reaction, it will require energy, so then we will put the energy term as part of the reactant. If we had done this as a separate term, the delta H here would be positive 285 kilojoules. Remember, endothermic reactions have positive enthalpy changes. The other example here, we have the energy term as part of the product. That tells us it was an exothermic reaction. And had we written it using method 2, the enthalpy change as a side term, the delta H here of the reaction would be negative 601.6 kilojoules. And the last way we can express enthalpy change is in the potential energy diagram. The potential energy diagram shows the potential energy, so the energy within the bonds, not due to the molecule's motion, between the reactants and the products. So if we have a endothermic reaction, the products have a greater energy than the reactants. So an example would be this type of potential energy diagram. Here the potential energy of the products is higher than the reactant. The enthalpy of reaction would be positive, if greater than 0. Conversely, if the reactant had more energy than the products, it would be an exothermic reaction, so that the delta H would be negative. Here is a better diagram of the potential energy diagram on the last slide. Again, for exothermic reactions, the delta H will be negative, is less than 0. And here, for endothermic reaction, the delta H is positive. The products have more potential energy than the reactants. Let's look at one final example where we have to incorporate the enthalpy terms in 4 different methods. Here in the words it says cell respiration is a series of exothermic reactions that takes place within the cells. If 1 mole of glucose is consumed during cell respiration to release 2,802 kilojoules of energy, express the standard enthalpy change for cell rest using the 4 methods. In our question, it tells us this number here is for every 1 mole of glucose. Therefore, our molar enthalpy of reaction for glucose is just this number, negative 2,802 kilojoules. If we're asked to write it as part of the equation, we would write the same number because there is only 1 mole of glucose in this reaction. If we're to ask to put this in terms of the product or a reactant, we would write the energy change as part of the product because this is an exothermic reaction, so the energy is a part of the product. And the last way to communicate this enthalpy change is through a potential energy diagram. We know that this is going to be an exothermic reaction, so the products have less energy than the reactants. So you should see a step down situation.